An inductor, called a coil, is a passive two-terminal component, a conductor or wire wound into a coil. Inductors find extensive usage in tuned circuits and in electronic filters to separate signals of different frequencies. An inductor has a characteristic known as inductance, where it sets up electromagnetic field when a current is passed through the coil. When the current is varied, the strength of the field varies. As a result, an electromotive force is induced in the coil. This may be expressed by the equation E is equal to minus m d phi by dt into 10 power minus 8 volts, where E is equal to EMF induced at any instant, N is the number of turns of the coil, and Q is the flux through the coil, and d by dt is the rate of change, differential with respect to time, of the flux. The direction of the induced EMF is always such as to oppose the change of current which is producing the induced voltage. In other words, the effect of the induced EMF is to assist in maintaining constant current and field. We may also express the relationship in the form E is equal to minus L di by dt, where all the values are expressed in practical units. E is equal to EMF induced at any instant in volts. L is equal to inductance in henries. I is the current in amperes, and di by dt, rate of change of current in amperes per second. The unit of inductance being too huge for electronic circuits, its submultiples of milli and microhenries are in the usage. Many inductors have magnetic core made of iron or ferrite inside the coil. Powdered iron cores, ferrite or part cores, are shown in figure that follows. Which serves to increase the magnetic field and thus its inductance value. The inductance L varies approximately with the square of the number of turns in the coil and may be increased considerably by inserting powdered iron or ferrite core. A range of inductors wound on toroidal or ring cores are displayed in figures that follow. Inductance in series. When inductances are connected in series, the total inductance is equal to the sum of the individual inductances, provided there is no mutual coupling between them. L is equal to L1 plus L2 plus L3, etc. Inductance in parallel. In parallel connection of inductors, the reciprocal of the resultant value of inductance is the sum of the reciprocals of individual inductances, provided there is no mutual coupling between them. 1 over L is equal to 1 over L1 plus 1 over L2 plus 1 over L3, etc. Inductance and resistance in series. If an ideal inductance is connected across an AC source, the voltage is given by equation E is equal to Em sin omega t. A current would flow having the same waveform at the supply voltage, but the current would lag 90 degrees behind the voltage. The inductance is said to have an inductive reactance XL. An opposition similar to that offered by a resistance to limit the current. The current can be shown by the expression IRMS is equal to ERMS over XL, which is also can be expressed as ERMS by omega L. The phase relationship between supply voltage and current can be shown by the vector diagram as in figure. EL is equal to I into XL, where EL is the voltage drop across the inductance, in this case same as supply voltage E. Every practical inductance has appreciable resistance, and we may draw the equivalent circuit of any practical inductor as an ideal inductor with a series resistance. If there is any other resistance in the circuit, it may be added to the resistance of the inductor to give the total resistance. If an alternating voltage is applied across L and R, refer figure. The vector diagram may be drawn as shown in figure. The current vector is first drawn to any convenient scale. The vector for the drop across R, ER, is then drawn in phase with the current. The voltage drop across L is then drawn as EL, which is equal to I into XL, so that I will lag behind the applied voltage by 90 degrees. The parallelogram is then completed to give the resultant E, which is equal to I into Z with a phase angle such that tan theta is equal to XL by R. Magnification factor of the inductance. The total power taken from the source is the power dissipated by the effective total resistance R in the circuit. There is no loss of power in an ideal inductance with zero resistance, although it draws current from the AC source. The power factor at any given frequency gives the ratio of the resistance of the coil to its impedance and may be used as a figure of merit of the coil. Q, the quality factor, is the ratio of reactance to resistance, which is equal to XL by R. This can also be expressed as omega L by R. The power factor is almost identical with its inverse of the coil called magnification factor or the quality factor, the Q of the coil. The impedance of the circuit. Impedance has already been introduced as a complex quantity having both a resistive and reactive component. Given by the symbol Z, we are therefore concerned not only with its magnitude but also with its phase angle. The unit of impedance also is ohms.